From the chart, we can see that battery have high energy density but low power density. This means that battery can store a lot of energy, but it takes so long to charge. Meanwhile, capacitor here show it has high power density but low energy density. So, to balance both, researchers have developed supercapacitor. They are designed to combine the high energy of battery and the fast charging of capacitor. But even now, the best performing material for supercapacitor is ruthenium oxide, which is very expensive and rare. Because of that, this study focuses on two cheaper and more available alternatives, which is nickel carbide and zinc carbide. Supercapacitor are mainly classified into three types based on how they store charge. The first type is EDLC, which store energy electrostatically without any chemical reaction. This usually involves materials like activated carbon. The energy is stored by the separation of charge at the electrode and electrolyte interface. The second type is pseudocapacitor. This is where nickel carbide and zinc carbide belong. Here, energy is stored through fast reversible redox reaction happening on the surface of the electrode. This gives higher specific capacitance compared to EDLC. And finally, we have hybrid capacitor, which combine both EDLC and pseudocapacitor behavior. Both nickel carbide and zinc carbide were prepared using the sol gel method, followed by drying and calcination at 350 Celsius. The only difference between them was the use of either nickel or zinc as the metal precursor. Then, the main focus of my study was to compare and analyze the physical-chemical and electrochemical properties of both materials using several characterization techniques. This slide shows XRD pattern of both nickel carbide and zinc carbide samples. From the graph, we can see that both materials show diffraction peaks that match the standard spinel structure based on JCPDS card. The main peak, especially at 311 plane, is the most intense for both materials. However, the peaks for nickel carbide are sharper and more intense, while those for zinc carbide are broader and slightly less defined. These tell us that nickel carbide has higher crystallinity, while zinc carbide has lower crystallinity. Sharper peaks with narrower width mean the crystals are more ordered and well formed. Broader peaks usually suggest smaller crystal domains and more structural imperfections. Now, moving on to the scanning electron microscopy SEM results, which reveal the surface morphology and grain size of both samples. Starting with nickel carbide, it shows a highly porous brain-like granular structure. The particles appear as fine grains, loosely packed and well distributed. The measured average grain size is around 0.62 microns. This porous structure increases the surface area, which allows better ion and electron diffusion during charge and discharge process. That's why such morphology is considered ideal for supercapacitor application. In contrast, zinc carbide shows a compact and dense structure which more tightly packs spherical grains. It has a larger average grain size of about 1.22 microns, meaning there is less surface exposure and fewer accessible active sites. Next is FTIR analysis, which help us understand the chemical bonding and confirm the metal-oxygen framework in both samples. Both nickel carbide and zinc carbide show absorption band in the fingerprint region, mainly between 550 to 670 per centimeter, which are typical of metal oxide bond in spinal structure. In nickel carbide, we observe three distinct metal oxide vibration bands which show the presence of both cobalt oxygen and nickel oxygen bonds in different coordination environments. This reflects higher structural complexity and a more developed spinal framework, which usually means more active redox sites and better electrochemical behavior. Meanwhile, in zinc carbide, the FTIR spectrum shows two main metal oxide peaks along with zinc-oxygen cobalt linkage. This suggests a more compact and less complex structure compared to nickel carbide, which could mean fewer redox active sites. Now is the cyclic photometry result, which give insight into the electrochemical behavior of both material, especially their redox activity and charge storage performance. Looking at the CV curve of nickel carbide, we can see sharper and more defined redox peaks, especially as the scan rate increases. These peaks are linked to the nickel 2+, nickel 3+, and cobalt 2+, cobalt 3+ redox couple, which dominate the pseudocapacitor behavior. The peak current also increases with scan rate, showing efficient and fast redox kinetics, good reversible and strong pseudocapacitance. Overall, this suggests that nickel carbide provides higher specific capacitance and better energy storage performance. In contrast, the CV curve of zinc carbide shows broader and weaker redox peaks, indicating less efficient pseudocapacitance from zinc 2+, zinc 3+, and cobalt 2+, cobalt 3+ transitions. The redox kinetics are slower and the response is less pronounced even as scan rate increases, which results in lower specific capacitance. In conclusion, this study successfully compared the physicochemical and electrochemical properties of nickel carbide and zinc carbide as electrode material for supercapacitor. Therefore, both nickel carbide and zinc carbide are promising supercapacitor, but nickel carbide has more advantage in terms of morphology and redox activity.